Okay, hello everyone. Sorry for the delay. I was having some issue with the microphone setup, so hopefully now it's all fixed. So let's do a sound check. If the sound is okay, please let me know. And image should be fine. All right. So today will be a little bit of an ad hoc testing with some cooling equipment. You can see the main part on the camera, so I can zoom in a little bit. Okay, audio is good. And today I'll do some quick experiments with Cryocooler and temperature response of transistor in best voltage reference on the market, which is Linear Technology's LTZ1000, and we'll see how it goes. So the idea is to capture response of this chip. It's had some connections from earlier testing. It's quite poor condition because it was also experimented with a liquid nitrogen bath. So some of the pins are corroded, and this chip definitely seen better days, but it's still functional inside. So we will redo the connections in here and attach it to the Cryocooler head here. I have already removed all the stuff we don't need. This is former STI Superfilter RX unit. So all we care about right now is the control electronics. It's on this other side of the case frame. And this is actual Cryocooler. There is a cooling fan over there, and the business end is this cold end tip right there. So that part will get very cold. And what we will do, we'll find a way to mount the chip to that cold end and connect another instrument I recently acquired, which is that guy over there with the blue display. That is Lakeshore 370 AC resistance bridge. Some of the people already probably seen the video about it, including the teardown. So we'll be using that today, hopefully, and see what results we can get. That is the idea. And this will not be a complete LTZ circuit. So I have the good old KX board right here. We will remove all that. We don't need actual LTZ circuit operation. If we just want to measure the parameters of transistor inside the LTZ, I'll need to actually do some wiring. I was hoping to do this before the live stream, but that didn't happen. So we'll do the actual wiring, and there is a small technique quirk in there, how to prevent a lot of thermal issues when doing with the cryogenic stuff, especially low power like this Cryocooler is capable. Originally there is a big vacuum insulated door, so I have took that apart before. I can show some pieces of it. And the reason for the vacuum insulation is to avoid any heat transfers. So this is the actual pieces of the door. It's a really strong stainless steel container. So it was like that, and this part was attached like so. So, and this is the flange interface that couples with the cryocooler. So I cut it all open, and actually some of the other bits are right there with all the electronics and super filters. So this is like huge copper block where everything was mounted. I don't think I'll be reusing this anytime soon, because this is quite thick stainless steel, and I don't have the welding equipment or means to put it all back together. So if somebody is interested, we can take a look in closer details how this was built. But for now, we will just do some crude insulation for the chip and deal with the temperatures and see how cold we can get. There is still all the original super filter electronics in this part. We'll actually need to have this connected, so it's a little bit fragile. So there are these bits. This is 3 filter assemblies. I have on XDEVs the full teardown, what's inside under these metal covers. The foil is for the radiation shielding. This is all SMC connectors that couple into those ports. This is, by the way, at the other end of the door, where all the SMA ports for input and output RF connections. And the reason why we need this connected is because there are temperature sensors on each of these blocks, and the electronics actually do need that temperature sensor to initialize and operate correctly. So we'll just have hang it from this connector. It's a very expensive micro dB connector. And to power the cryocooler, we need 24 volts or 27 volts. I don't remember exactly. I'll need to check that one out from this DC input jack. Yeah, it's 27 volts DC. So I'll just use HP 6653 power supply right over here. It have ability to provide up to 35 volts, 15 amps, more than enough to power this beast. So I'll do the connections and all that, and if any questions, let me know. I think we can start with hooking up all the wiring, and then we can continue with attaching LTZ chip to this gray cable, which is attached to Lakeshore AC resistance bridge. So even without the cryocooler operating, we should see the LTZ temperature from the silicon junction of the sensing transistor. And once that is ready, then we can worry how we attach everything to the cold tip and figure out the next step. Let's move this stuff to the side. We will also maybe try to drive the heater from Lakeshore as well. By heater I mean LTZ onboard heater. I have this SMA connector to BNC adapter. So this is the heater output from the Lakeshore. Perhaps I can change lens to macro lens, and we can see the condition of this poor LTZ reference. Before I start disconnecting and connecting wiring, let's do that. You can also see the closer look on the Cryocooler flange. So this was just for some quick tests. I was using the foam insulation with the foil, aluminum foil, and cardboard tube, which exactly fits the cold tip diameter. So we do have, actually, I can move this like so. There are mount holes with a thread. It's like really small thread, like maybe like M2.5 or so. We could use that to attach some kind of, I don't know, maybe a piece of FR4 board with some holes on the side, and we can keep the LTZ case in the tight contact with cold tip. And I do actually have some screws that would fit those holes. Let's see. They're like super tiny hex head screws. They also used in the super filter assembly inside the dewar. Oops. I think I'll need some better tools to handle those tiny screws. So that's the one, for example. Zoom in a little bit more. There we are. That should give a nice close look. And let's see if we have, yeah. I was thinking maybe I could cut one of the KX references to get the, like a piece of PCB that I would be able to mount with those tiny screws, but I think the total thickness would not allow to do that, which is okay. We can find alternative way. Also, you can see how bad this poor LTZ chip was. all the bunch of corrosion, some pin missing, and just for the sake of clarity, this was LTZ1000 CH, date code 2016, week 49. Right. Now the main trick with cryo-cooled assemblies and stuff like that is to avoid any unnecessary thermal contact with outside world. So like you want to have the component that need to be cooled to very low temperatures, but you don't want to also have a lot of heat to get into that assembly. So like when you use normal electronics and normal connections, you would maybe use like large connectors, thick wires, stuff like that. And all of those are essentially heat transferring devices. And if you have some massive amount of connections from, let's say, you have like these big thick wires coming from LTZ chip, which is cryo-cooled to low temperatures, you will have a lot of heat transferring to this chip, and it will prevent reaching ultimately lowest possible temperatures, because Cryocooler now will need to cool not just the chip itself, but also the wiring and all the additional mass that is attached to our DUT itself. So this thick copper wire is a quite good thermal conductor. That's why on the Cryocooler you see often some special wiring and a lot of like radiation shields, which look like it could either be foils or special copper blocks mounted to the other parts of Cryocooler. Those all serve purpose for correct thermal management inside of the system, because again, these closed loop cryocoolers, they don't have much of the power capacity. So yes, they can reach very low temperatures like minus 200 degrees centigrade, which is like 72 or 75 kelvins, or even lower, like the multi-stage cryocoolers. But the heat capacity for these coolers usually is just few watts. So like if you have a few watts transferred from hardware to the cryocooler, it will not be able to remove that heat, and the temperatures will keep going up and up and up, and that is very undesired behavior. That's why on the original assembly with the super filter, you see all this big massive copper blocks with all the electronics inside, but the connection between that copper blocks to the room temperature chamber connectors, those are super tiny wire. There is like gauge 40, 42, 44, maybe even 46 in the coiled matter, those are the connections to the room temperature part of the door. So they are like almost a hair thick, and the reason why they coiled like that is to first like decouple some vibration from the cryocooled assembly like this, but also to increase the length, so the heat would need to travel more distance before it reaches the cold assembly. So obviously for the electronics it may not be optimal, because you have the long thin wire which have additional resistance, some additional loss, stuff like that, but this is the paramount for excellent performance cryocooling and cryocooling requirements in assemblies like that. So that's the basics of electronics assembly when working with limited power budget with very cold temperatures. So let's go back to our LTZ chip, and to attach it I will follow the similar concept by using super tiny wire which we can salvage from relay coil. This is one of those tiny relays that I just took apart to steal the, so this is the case of that relay. This is a DS2E latching relay, well it was, which I destroyed to get the wire from it. I like this wire because it's also insulated, so we can twist and wrap it around stuff and not worry about electrical shorts. So we'll need to clean up that LTZ a little and then attach some wiring for it. Let's see. So there is one pin damage in here. It's actually missing. But I don't need all the pins. And there is some glue there. I think we will need to cut some other pins we don't really care about. And probably under the microscope we should attach to that damaged missing wire. I cannot even see the metal. Yeah, there is that metal. There is also a lot of some flux residue and some stuff. We will need to clean all that a little bit. And the reason why it's so badly damaged is running the cryogenics with the access to air, and as you may know, air have a lot of condensate, all the vapors, like mostly water vapor, in the air that is causing humidity, and then that condensate is when you subject air to very cold objects, it will form ice and snow, and because of the salts and other stuff also present in the air, that will be slightly conductive, and when powered electronics is covered with that layer of ice, snow and salts, it will corrode all the powered parts and will cause a lot of issues like that, like you see on this poor chip. That is one of the reasons why any damaged electronics with water ingress is quite challenging to repair, especially if the device was under power and submerged in salty water like ocean water, sea water. That essentially kills any unprotected electronic device and electronic assembly beyond any economical repair. So unlike popular myths like putting a lot of rice on the PCB or the phone or stuff like that, or the laptop, that wouldn't help. But what would help is removing the power as soon as possible, and then trying to get all the water as much as possible out. But obviously with today electronics, that can be almost impossible, especially with the phones and stuff, because they have battery permanently attached and you have no ways to remove the power source without destroying the device even further. So hopefully the right of repair will get forward traction and we can see more serviceable devices in future. So I think I'll need to clean up a little bit more, and then we will need to take a look on the microscope how the chip looks and start attaching some wires to it. Okay. And the actual circuit that I would be trying to replicate, let me open up the schematics that I just prepared. It's very simple, so no rocket science. Let's see if I can share the screen. Not that. There is the circuit. So it's essentially, let's move this there. Yep. So this is the idea that we will run. So it's quite simple. In essence, we have the heater connection, which is that LTZ pins 1 and 2 together with external diode, which is standard 4148, connected to the heater output of Lakeshore 370, and then we have the transistor used for temperature sensing. It's connected to pins 6, 8 and 7, and 7 pin is internally connected to other transistor as well inside of the LTZ chip. So we have here 4 signals. Essentially we will use just 4, it's 8 signals, because Lakeshore provides guard for each of the voltage sense positive, voltage sense negative, current source positive, current source negative, but we will be connecting just simple voltage sense, which is this thin red line, together with sine line. They will be connected through separate wires coming directly to pin 8 and pin 7 of the LTZ package, and then we'll have the current source connected to I plus to pin 6 and pin 8, and also I minus, which is current return, connected to the common of the schematics. This will give us so-called diode connection for transistor, so we can use this transistor essentially as a temperature sensor, because silicon junction have a typical temperature coefficient around -2 millivolts per degree, so we can actually change the temperature and measure the output voltage, and if we have calibrated sensor or we know the calibrated curve, we can make the very good measurement of the temperature of this transistor die. That is the idea, and LTZ reference is rated for temperatures from, I think, -55 to positive like 150 or something like that. I don't exactly remember from the data sheet, but it's available information. But there is no information, at least not easily available information online, about what happens if you have temperature below -55 centigrade. For example, if you have 70 Kelvin temperature, which is -196, and there is also a couple other interesting outcomes of that. But if we can capture the temperature response of this transistor going below rated temperatures, we can see if it's reproducible, how hard is the slope, and I think that will be interesting. Obviously, I don't really care if this chip dies, because it's already quite damaged, and it wouldn't be use for any like low drift or high precision reference. It's essentially an experiment beater, so we would not really cry if it dies, but hopefully we can get some good data out of it. That is the idea, and I'll hook the camera to the microscope so we can see the wiring and hopefully get some almost there. All right. One, two. Audio should be fine, I hope. Audio check, 1, 2, 3. Everything looks good on my end in terms of audio. 1, 2, 3. Okay. So here we have our poor chip. It looks like I would be able to solder to this pad remnant, hopefully. So let's trim the other pins a bit. I don't need them so long. There we go. And here is that super thin wire. So to compare it against the pin, it's like maybe like 10 times smaller in diameter or so. Pretty cool. Let's see if we can clean this glue around. I think it's just flux. Other pins look fine. Let's apply some IPA. Okay, we can try to solder a piece of wire there. think I'll just use some of the glue so the chip doesn't move. And let's see if the solder sticks to it. And yes, usually the packages like this are hermetic and glass sealed, and that's one of the reasons why such wires, such pins, are made from not copper but from cover, which have the same thermal coefficient of expansion as yeah, I think I can solder to that pin, no problems. So the cover have the same mechanical thermal coefficient of expansion as the glass. So when you subject the package to different temperature variations, the connection between the pin and glass seal will not break, providing the good hermetical way to exit signals from package to external world. So and yes, we can indeed wrap our wire around the pin, solder it nicely, and there we have it. This is just an experiment. I don't even know if I need this pin or not, but I like the connection. So let's mark the pins that we do need and get them connected. Acetone works for flux pretty good too. I often use it as well, and especially like if there is a lot of flux, then acetone can be very helpful. But you need to be careful because a lot of acetones may have some additives that may leave some residue on the surface. So if I really care about clean PCB surface, I would use IPA after the first acetone clean. Alright, let's get back to our pin definition. So we need to connect wires to pin 1, 2 and pins 7, 6, 7 and 8. So essentially there will be 5 wires coming out of this LTZ chip. We can open the data sheet, bottom view. So we have 1, 2 heater and then 6, 7, 8 on the opposite side. Okay. Let's orient the chip. Essentially we will need the wires at this pin, and these 3. We actually don't even care about that missing pin. It will not be used. Makes our job easier. No problem there. There's our heater. So I think I'll give like around maybe 15 centimeters of wire. That will give us enough distance to add a lot of insulation before we attach stuff to Cryocooler. So there is our second wire. This is a heater connections. And now it's time to add our temperature sensor transistor connections. 3 wires. I need to be quite careful with these tiny wires because they are easy to rip off. And this is good enough. 3 done, 2 more to go. To be honest, I don't even have exact confidence that this chip is really working. So we can check the heater resistance to see if it's at least in the correct ballpark. I think should be a couple 100 ohms, maybe less. And actually I also think I do need to have 2 wires connected to the transistor end, because I have the voltage sense and also the current source. So let's do that. So we have pin number 8. Let's go back to our schematics again. Pin number 8 is the collector of Q2. Yes, this pin number 8 need to be connected to pin number 6 on the package, and then we have 2 wires coming out of the common joint, and then pin number 7 we also need 2 wires. Okay, we can do that. Also we need a diode for the heater, so let's check the resistance before we go ahead with diode. So for this I'll just use Fluke 87. You can see the huge probes compared with the pins. There we go, 247 ohms, so the heater is still good. Let's connect a diode right here. I should have 41, 40, 48 diodes somewhere around this lab. I also think that diode will change the parameters when cold, but for the heater that probably wouldn't make any major problem. Let's see, diodes. Want to use the small SMD diode, so we can minimize the number of external wiring and connections. Diodes, there should be a box with a bunch of them. Okay, I think I found it. SMD, Zener diodes. We can probably even use some LED, but it will be all insulated, so we wouldn't even see anything. Okay, I think I found some. Little tiny diode. So we need diode connected to pin 2 and node to pin 2. Anode to pin 2. There is our pin 2. Let's desolder the wire. There is our anode. This diode is kind of big and bulky. There we go. just move it slightly. I need to be careful not to put any solder on the case there, so we don't want to. Yeah, I think there we are. Come on. We can bend this pin slightly out of the way. And now we can connect the other end. It's kind of a 3D package. There we are. So this is our heater. The purpose for the diode is to prevent opposite polarity voltage on the substrate. So that external diode gives additional voltage drop to avoid that situation. So we need to have pin 8 and pin 6 together. We can do that like so. And then we need to add extra wire. And that should have good connection. Let's see, where should we read the sense exactly? Okay, we need sense connected to pin 7 and pin 8. And pin 6 we don't really care about. Okay. So the pin 8 is this higher one, marked with a notch, and pin 6 is this one. So we need to redo the connection. And while I'm at it, I might just add this little bit of flux, just a little bit, to make the process easier. There we have it. There is pin 8. Now we need to have another 2 wires. To the pin 7, and then we can attach this stuff to our lakeshore wiring and see if we can get any meaningful readings out of it. Whoops. That is our pin 7. It's not going anywhere. I believe I need to swap the battery in the microphone. It's already blinking at me. Sound check. 1, 2. 1, 2, 3. Okay. I think most of the viewers probably already sleeping by now. This isn't very exciting, but I rarely have time for the nice and polished video, so we have to deal with this live stream stuff. I do have a couple ideas for videos, and actually one of them will be Keith Lee instrument repair, but I'm still waiting for some parts for it. So this is our chip with all the wiring, so we'll need to figure out all the mapping. Let's remove that piece of solder. There it is. This is for comparison, the original pin. I can put some other stuff. Like for example, I don't know, BNC connector, but I guess everybody seen the LTZ1000 package. This is the capacitor, 470 microfarad, just for the sake of size comparison. Okay. So now we need to do the connections on Lakeshore. Oh, and one thing that we forgot is to connect pin 7 to the diode cathode, because that's our common ground. I think that would be a good idea to do as well. So let's do that. It's pin 7, right? Yeah, pin 7 to cathode of the diode. I think I can actually use this piece of the remaining pin to do the connection. It will give us low impedance-ish ground. Like so. I think that, okay, that may work. Now if we can bend it a little bit, I think we will be golden then. There we are. Oh, pin 7. So that should be go up. Okay. I can put a solder block over there. Try not to desolder other stuff. There we are. That pin is not touching anything. Now the next step is doing the connections to big cable. But I think before we do that, we should mount the chip on the cryocooler end, so we don't risk ripping apart stuff while we're doing the wiring. So okay. Camera is back. So that we need to connect to this cable. And here is our chip. And let's see what we can do in here. We obviously cannot glue it, because the glue will rip apart and fall off because of the big temperature change. What other options we have? We can make some kind of a bracket from dielectric material and then have 2 screws mounted on the opposite ends, and they will hold down the LTZ chip towards the cooler. I think that would be probably easiest and quickest solution. And the question is if I have something suitable. Should be something dielectric, like a piece of plastic. And not very thick. Because those screws are kind of tiny, so this would be definitely too thick. Let's try something thinner. I have another possible option is using some copper wire to make kind of like 3D shaped surface. It's not very strong, so I'm concerned that under the mechanical pressure it may get loose, and then we will lose the contact with the cooler part. What other options we have? I have actually steel cover. It's actually not steel. It's silver plated. This cover it comes from the Cryocooler assembly, from this unit, from the door. It's quite thin. You can see like how I can bend it, and it's spot welded on the corners, so I could cut with the scissors, cut some shape like a plate, and bend it, so like drill 2 holes in it and bend it so it will apply the pressure to the chip, holding it down to the cold end surface. And it's not like that I don't need this cover for anything. I have 3 of them, so probably we can do that. At least I don't have any other better idea for time being. Let's see. Let me check under the microscope if it's copper or not. It cuts very easily. It might be copper. I can see kind of pinkish edge. Maybe brass. Definitely pinkish on the cut edge. So let's see, we can start with the square first. It's obviously metal and conductive, so we'll need to add some padding. So we can do the circle. Kind of a circle. And then we will need to measure the distance to add those holes for screws. Let's see what's the distance between the two of the mount places. I don't have a 3D printer, so there would be no 3D printing anything in this lab. So let's see, we need around 17 millimeters. So let's mark 17 millimeters. Somewhere there. Good enough. We can do little drilling. If I have the drill that small, let's see, maybe I can just punch it with something sharp. If it's copper, it should give away. Or I can just cut it with my end mill. Okay, I have 2 holes. They're kind of small, but we will make them bigger. Definitely looks like copper. Soft, drills easily. Let's see if the screw can go through. Probably need slightly bigger. Yeah. Okay, 2 nice holes. Let's see again. Yep, we got one in and the second one. Okay. So the idea is we can actually cut the hole to match the LTZ outer ring without touching the pins. But that would need some precision work. So let's see. Yeah, the diameter is around 8, 23. I'm not sure that would work. Let's see if I can. Have enough room to bend the chip in this, bend the plate in the center. Oops. Let's see. I don't want to strip the threads, so I need to be kind of careful. There we are. Just bend a bit, not too much. This is a little bit tricky. Maybe I do have to cut the hole around for the LTZ chip. Yeah, that will be probably faster. We need 8.2-ish, let's say 815 millimeters in diameter. Somewhere around the center. Let's do that. Let's do that. Now I need some bigger drill. Now I need to find the drill. I've seen it recently. Here it is. But where is the battery for it? There it is. Screws. So I'll use just a step drill, nothing fancy. So we need something to drill on. I don't want an extra hole in my bench. Let's see, I should have some piece of wood. Yeah, this should do it. I think I'll go other way. So this is around 7. Let's see if this is enough. Let's see if this is enough. I don't think it is. Actually, I can use the different package, different chip. So this is, let's zoom in a bit. This is another T09 package. It's, let's see if you guys know what it is. Have the label says VFR and the number is 322013. So that's the part number. What this is? Any of you guys know? Yeah, I think this will work. What is VFR 322013? Ah, that's no fun. Now let's see if we can put the chip in our carrier. I can even solder it, probably, because this is a copper, maybe like silver plated copper. Then it will not go anywhere. Oh man, we get stuck in here. There we are. To get all these wires through, let's cut the excess. There we are. I might need to remove the diode. Whoop. Or maybe not. Yeah, look at that. That's pretty good. That is pretty good. Let's see. let's mount it. And then we can do the wiring. Okay. I was looking for this. So the top. Then we will need to insulate all this, but probably after we do the connections. Okay, now let's do the alignment for the chip. Mounting bracket. Let me remove the CPL. Stuck well. Okay. There is our close-up shot. Looks ugly. Looks ugly. Okay. It's quite robust. Could probably make it like smaller, but it's too late now. Yep, it's not going to move there, I hope. So now let's clean up the wires, mark them, then we can see what happens. I think I'll just tape it down right next to here and write down which wire what meaning have. Oh boy. This is a heater. And that is also a heater. We can separate them that way. This is our top. There we are. Need to leave it some slack. So this is connection to pin number 7. Pin 7. Pin 6 and pin 8. So the 2 is pin 7. This is I minus and V minus. Now we need to connect pin number 6 and pin number 8. Pin number 8, which is our actually pin number 8 is our VSense Plus, V plus. Now we need to have the bottom. This is I plus, current source positive. And now we just have a heater left. Here is the heater. Heater plus, and here is the heater return. Heater minus. Okay. Now we need to insulate all of this somehow. But let's do the connections and check first that it still works. Actually, it's hard to see, but I put all the labels in here. So we can do a wiring. If any questions about any stuff, feel free to ask. I'm checking the live stream chat from time to time. Now I can do the this was the cable from the power meter, Agilent power meter, but I don't have RF sensors, I don't have the power meter, so I just sacrifice this cable because it have double shielding. I was hoping for 8 wires inside of it, but it have only 6, so no guarding for this application, sadly. But I think we are not going to have very slow voltage signals, maybe a couple millivolts, so it should be okay. It's a nice cable otherwise. Have actually separate shielded part and then the 3 wires coming out. Nice reinforced braid. Actually, I need more. There we are. So I need to connect that to all that, and we'll see what we get. So let's solder our connections. I will not even bother with the insulation and braid or any of that. I'll just hook everything together, tape it down to a table, and so we can see what measurements we can get. So I'll not connect the heater because heater is the separate cable. Let's connect eye source. So where is the writing? Which color means what? Here we are. So blue is V minus. Okay. Pin 7. Pin 7, V minus. Then we have I minus orange. I minus to orange. Then we have I plus to red. There we go. That's a little bit too much. To red. Then we have, there is the heater. We have V plus sense to green. V plus to green. Now we have V guard. We don't use this. And yellow is I guard. We also don't use it. So we don't need these two. And everything else seems to be connected. So let's tape it down. Like so. I don't need these two. Also maybe just a little bit of more space between these guys. There we are. Let's power on the bridge. See what it shows. Shows nothing. Says increased excitation. I can zoom in on the display. Do voltage current excitation, current mode, 100 picoamps, one nanoamp, Let's go maybe 100 nanoamps. Okay, it says decrease. 31 nanoamp. Outer range is off. LNM, I'm not sure what is LNM. Let's actually see if I can get some voltage readout maybe. So control setup. I'm not really played much with the unit. I think we have open loop. Actually we have off because we don't control anything yet. Zone setup, zone 1. Set point, that doesn't matter. That's PID settings. Heater off. Should be sensor settings. And now look, input setup. I think change post time. Select width. Let's go user curve, no curve. Temperature coefficient. Positive, negative. I think negative. Instrument setup. Have different frequency. Common mode reduction. Guard drive off. Monitor output. Current sense positive. Current sense negative. Voltage VAD. What's the VAD? Okay. Where was range? Let's see voltage mode. Okay, that's I think we need to use the current mode. Or we need to read the instruction. Let me rearrange the setup a bit. I think we need to change our readout to some other units. Let's see, we have input setup. No curve. No positive, doesn't change anything. Instrument setup. CS positive. see, display setup, I think that's what it is. Display location, ohms. Let's see, here we have ohms. What else we have? Kelvin. No curve, okay. Let's give it some curve. Temperature under. Temperature under. Is there linear linear equation? Okay, so ln means linear, I guess. Monitor output. I think that's the output on the back. We don't need that. Display setup. Let's see, linear. Let's try another location. 2, 1 ohms. Okay, now I have just two of the same. I'm not sure if there is a mode, oops, to actually just show the voltage. Kelvin. Ohms na Kelvin. Yeah, we can set all the curve values. So this is, I believe, for NTC. Yes, we don't need that. Instrument setup. Resistance range. We need to select diode sensor, not the actually, I'm not sure if this instrument does work with diodes. It should be. Let's see, control setup. Because if it's resistance only, then we might not be able to do much. And it is input setup. Display setup. What is max? Okay. 3, 2, linear. Let me just double check in the manual real quick, because if it doesn't read diodes, then we will have to use a different instrument. Because I know for the fact that my temperature monitor works with the diodes, so I can remove these LTZ modules. Put this guy over here. So this guy on top, temperature controller, does support diodes. So let me double check. Or maybe anybody can open up a datasheet for Lakeshore 370 and see how to configure it to read out silicon diodes. So let's see, 370 features resistance measurement ranges from 2 milliohms to 2 megaohms, 21 excitation levels from 3.16 picoamps to 31 milliamps, sensor input, PID control, unique noise reduction elements. I think it doesn't read any diodes. This is a purely resistance bridge. Okay. I guess I should have read manual before I started all the connections and everything. Okay, we'll have to use 331, which is okay too. We'll just need to redo the wiring. Let's see, I can set maybe 10 microamps and see what happens with that. Display setup, number of locations, display location 2, ohms, Kelvin, ohms. Display locations 1, minimum, display location 3, linear, current, increase resistance, ten microamps. Yeah, it doesn't work. Okay, well, let's redo the wiring for 331. I'll have to disconnect stuff on the back. Actually, the wiring is the same. No, not the same. There is one connector, and this guy uses two connectors. So I'll have to redo some connections in here, which is all right. Yes, indeed, searching for diodes does not give any results. So I guess it's fail on me by not learning about the instrument I have. I was assuming that Lakeshore makes actually units compatible kind of with all the sensors, but apparently this is a resistance bridge, not the temperature bridge, so it does not support diodes. There we go. So I'll have to redo the... I could make a new cable, but it's not going to use this one for this case now. So I could just do the proper cable for temperature monitor. Let's unbend this. And unbend this. So let's have this. Put this small cable through there. And then this the whole stuff. Get over there. So let's probably disconnect everything first, and then we do the connection with the new wire map. Go. So the connectors plugs like so. So I current, there is no guardian here, makes stuff easier. So we have pin number 1 I minus, which is orange. So we have orange. Next one is V minus, which is blue. Okay, let's do this orange. It'd be nice if I would have something like, yeah. Now we have blue. Then we have bottom is, I believe, shield. Shield it is. Then V plus. V plus is green. Then we have I plus, which is red. Red, I say. And then the rest is not connected to any stuff. We can just put it in there. Let's add a little bit of tape. Just to see that it works. Now we need to connect the power. And sadly there is no GPIB from this unit, only RS232, so I'll have to do the login measurement some other time, so we can at least see that it's doing what it's supposed to do. Let's power the thing on. Okay, here a good beep. Okay, and we reach some temperature. Let's check the configuration. Input setup, input A. So we need silicon diode. And display setup, location 1, input A, No curve. Okay, input setup. Curve. Let's do. Okay. Display location 1. Input. So that's the voltage over it, I think. We can measure voltage with DMM. Let's see the display location 2. Input A. Temperature C. Display location 3. Input A. Linear. Display location 4. Input A. Sensor. It's the same one, okay. Heater out. Let's set the curve. Input setup. Can try that. Temperature over. Heater power. Let's see curve. Edit curve. So there are some thermocouples. Type T, type E, type K. Let's see this curve DT670, which is the native lakeshore temperature sensor. Serial code format, voltage per Kelvin, SP limit, temperature coefficient. So this is the temperatures and voltages. So 320 kelvins. Okay, we need to have around 500 millivolts for that. That's why it says over, because we are not even that. We could be reverse biased, so that could be an issue. And let's go back and see what we are actually reading, if the polarity is correct. We can use one of the DMMs on the bench to check that. Let me get out of the light reflection. So we can see from the 2002 which voltage we are reading on our points. So we have V minus this pin, and then V I plus, I believe, yes, I plus and I minus. Let's do that. So we are indeed reading 563 millivolts, which does sound a bit interesting. Oh, I broke one of the connections. Maybe I wasn't really connected there. Let's redo that. So we have V minus V plus. Indeed 21, so it's correct reading. Let's change something up a bit. Plus, read over here. Okay, so this does sound a little bit different. We can also check the current. Let's do some more voltage measurements with the V minus. It's this pin. That is quite interesting. Let's see if we have no curve. Okay, that is more to the truth. Whoop. Let's see. Curve is not here. Okay, so if no curve, then there is no temperature. Okay, makes sense. With DT470 we have some other. This looks like we can try to cool it a little. See what happens. 25, we can use the soldering iron to heat the chip a little and see if the temperature goes up. Let's try that. I'll just touch it like on the side. It's hard to get there. Yep, temperature does go up, so at least we have direction correct. So let's configure this display to show in kelvins. Display location 3. Source temperature Kelvin. And then do the insulation and fire it up. It's already quite late, so I don't have much time to go on. And the question is, yes, that will be the part for another video, but I was doing some vacuum stuff for this cryogenics experiments, and I was using the Piranha gauge, active Piranha gauge from Edwards. So I write a simple Python script for LTZ1000, so I can get the readout in millibars to see what's the vacuum reading is. Essentially, we'll get back even in the experiment like this with vacuum chamber. I already have some ideas what we can build here. So we can mount small PCBs with different voltage references, op-amps, analog to digital converters, digital to analog converters, different resistors, stuff like that. And it would be vacuum evacuated, so there will be no air, no condensation, no issues related to that, and we can reach lower temperatures and test behavior of different components at cryogenic temperatures. So that will be all. Okay, we can do the wiring for Cryocooler. So now we need to connect the power supply. There was a wire going down there. To remove the solder from these terminals. I need a bigger tip for this. Cool. Good enough. There's just screw terminals in there. So, okay. This cooler is produced like that. Fan is not very good state. So it's kind of noisy. Oh, come on. You can do it. It's kind of fun. Like I have this heavy gauge wiring in here, and then the small tiny wire coming out. Okay, we have the power supply connected. Let's connect the electronics, otherwise the onboard systems goes crazy and does not let the cryocooler to be started. I also want to write my own Python program to control this cryocooler guy, so we can do all the fancy stuff with the graphing and everything, real-time temperature readout. There is quite a bit of control and sensors all around, like reading the power parameters, VFD drive, settings, all that stuff. So I think we have, let me reposition the camera. You can actually see the vacuum pump in the shot. This thing with the hose on the right side, that is the vacuum pump. So I'll start with this shot, and we can do the close-up later. I still need to do in the installation. I just want to have the quick power on, so we can see the temperature drops a little bit. So let's see. Okay, are you guys ready? The moment of truth. If I can only find my RS232 cable to hook up to Cryocooler port, that would be nice. I just saw it recently. Because I don't think I'll be able to ramp up the power for Cryocooler without the software control. So we do need that cable. We do need that cable. It's essentially USB to UART, so nothing fancy. Nothing fancy. See a lot of GPIB cables. It's not on the bench, so that's that. Could be hidden anywhere. Anywhere over there. Cable, hello, where you are? Oh, I think I know where it is. Or maybe not. No, it's not here. I thought it's near my temperature chamber stuff. But let's check again. Yeah, there is just USB connection. So that's not it. That sucks. Oh, here it is. I found it. Was on the most obvious spot, just right in front of me. Yes, it's like the physics package. It's essentially right now it's using just a temperature sensor, so there is nothing fancy about it. I just didn't figure out which of the temperature sensor it's using, so I actually didn't spend any time on that. And I wanted actually to take the response of the original temperature sensor, because it was calibrated for 70 kelvins or so. So we can kind of guesstimate what the response of their sensor is, and test with other diodes and transistors, including this LTZ. So having somewhat calibrated a cryogenic sensor instead of no sensor at all was kind of useful idea, I think. So we are ready to go. Let's program some stuff and supply 27 volts or thereabout. Okay. I'm just checking, making sure everything is properly connected. I also need to remember the password for that, for the application. There's our power supply, 27 volts. STI application, where you are. So output voltage 27 volts, current let's say 12 amps. Output on. Okay, so there is that. But we have some crazy noise going on. For the temperature. So that's the first problem. It does seem to go down. So we're going to the right direction. Let's see the state, cool down. Cooler is right now using 20 watts. Fan is kind of loud, so I do want to get it water cooled, so it's reasonable for the noise use. Let's turn off the Cryocooler and see if the temperature goes to normal, because I already see the snow there. So yes, our connections here not quite right, and we did get already some snow. So let me show you in a better picture what I'm talking about. So, evil condensate. You can see it's all water around, and behind that there is a snow there. So we'll have to use the heat gun to dry it a little and then do the insulation. I also see crazy jumping just from the heat gunning. So, go figure. I didn't realize that it should be that sensitive. For the noise and stuff like that. Let's do some insulation. This wouldn't help too much, but at least would slow down condensate a little bit. Okay, I guess we can just let it go for a little while. There we are. Fan is on, power is on. Why 13 volts? 27 volts. I think somebody's controlling my power supply. Okay. Try again. Voltage 27, current 13 amps, output on. Okay, cooler is on. I wonder how loud is it on the microphone here. So sorry about the noise. enter password, status. So Cryocooler is using right now 20 watts, 7.3 volts RMS, 2.72 amps real current, and PWM drive 47%. PWM frequency 60.86 Hertz for this unit. I wonder if there is any setting for the averaging or something, so we can see more stable readings for temperature in here. Let me get the camera straight. So there is the power supply readout. So I turn off fan, turn on fan. Noise going crazy. I guess we can just leave it running for a little bit. Any questions for now? I guess for the next time I can do the proper shielded cable. Definitely better insulation setup, so we can do the good LTZ mount. What else we can do? I probably will be using different Cryocooler as well with vacuum insulation, because I have already a different unit which have the vacuum chamber on it, but it needs some little bit more preparation work, so that definitely will be much better results. I can stop the cryocooler now, so we can see stable temperature at this point. So, okay, we reached around minus 90 degrees, which is 182 kelvins. If we believe that reading, at least the voltage is 0.81 volts, so around 800 millivolts. And we can see like actually how the temperature is going up and up. Let's power on again. I think it needs around 20 minutes, 25 minutes to reach to around 80 Kelvin. But probably with this junk insulation, it will take more time. That jumping around definitely not very nice. Let's actually connect the 2002 and see if the voltage actually more stable, or is it actually the voltage jumping around and just some common mode coupling with the lakeshore meter. It still does quite jumpy, but it's actually settled down when I hooked up the 2002. Oops. So you can see the jumps around 20 millivolts, which is quite a bit. Okay. Should we turn off the cryocooler to see what's the reading now? I think so. So we get to minus 112 centigrade, which is 161 Kelvin, if we believe this readout with the curve from GT670 sensor, and absolute reading is 0.862 volts. So Keithley agrees pretty much to the same value, so 855 millivolts, and we get around the same over there. Let's power back on. Another reason why I actually want to measure the response of the temperature sensor in the LTZ is I would need to know what voltage I need to regulate in the circuit. Like when using the LTZ reference circuit from datasheet, you have the op-amp and 12.5K to 1K divider to set the operating temperature range. So essentially that circuit together with the LTZ temperature sensor defines oven temperature for the whole reference. And if I want to be using reference at cryocool temperatures, I would need to know which voltage to stabilize, so I can calculate what's the resistor value, resistor divider value would be to maintain, let's say, few degrees higher temperature than the cryocooler minimum temperature. So we can have both benefits from super cold operation and onboard oven precision control. At least that's the idea. Okay, we're ramping up the power, 41 watts at the cryocooler now. PWM drive is around 60%. Watts, 63% PWM drive. The rejection temperature is 40 degrees. I think I'll keep it running for maybe 10 more minutes. And then we will record the final temperature, and I can program the Keithley meter to record the voltage, so we can at least get a curve out of that, and then we can call it a day. 65% PWM drive, 60 watts power. .75 watts power, 72% PWM drive. So Cryocooler is using 77 watts, 11.4 volts, 6.8, 6.9 amps. Current phase 26 degrees. Current RMS 8 amps. We're almost at 1 volt. From the LTZ chip. Power is 88 watts, 77% PWM drive. Now in the normal condition with the Cryocooler attached to the vacuum insulated chamber, it's using about 90 watts of power to reach to the cool down temperature, which is normally like 77 Kelvin. And after that, the power drops down to around 30 to 35 watts because it just maintains that cold temperature. Doesn't need much power, definitely don't need full power to keep it. So essentially this Cryocooler is able to reach temperatures around like 60 Kelvin or below, a little bit below, if it's run without load and with the proper vacuum insulated GUR without heat loss. Obviously this is not the case now with all this very ugly quick setup, and I already start to see quite a bit of condensate over there. So I think we are pretty close to the low temperatures, and I'm already logging the data. To show the power supply readout. So almost 1 volt, and the power is Peak, I would say around 8 amps. We can bump the power to maybe 100 watts, and then we can prepare to turn off. Let's see the magical 1 volt. Yep. I think the actual voltage is slightly lower. When I turn off the cryocooler, we should see that. Doesn't look like it wants to go any lower, so I guess we can turn it off and record the warm-up cycle. Also, to avoid damage to cryocooler, I gradually reduce power now, and only when it reaches around 40 watts or like 35 watts, then I will remove the power, because the displacer is cold now, and if you turn off the power suddenly, it may add extra wear to it. Now power is 37 watts. I'm dropping 57. 44 watts. Now you can see quite a bit of snow. Okay, cooler is off, and the temperature is actually higher. Huh. Okay. I think we'll have to investigate the noise issue so we can get a nice stable readouts. You can see how quickly temperature goes up because we have just a very little thermal mass there, and all the heat from the ambient is now coming back into the cold parts. So it looks like we need around 1 volt set point for temperatures around minus 180 degrees centigrade, and can plot some more curves, but so far look promising. Any questions? Any comments? Let me know in the comments. Feel free to ask anything you would like to see in future videos. And I'll be publishing some test results and this more details about this experiment on EV Block forum in metrology section within next days, and hopefully we'll see more refined and better results in future. I also have article about Lakeshore 331 temperature controller designed specifically for cryogenic applications, and as well as common article about Lakeshore 370 AC bridge. Obviously I'll need to learn its use a little bit more. As well as some vacuum stuff and thermal insulation and more Cryocooler goodies. It's almost around minus 100. There we have minus 100 centigrade, 172 Kelvin. If we believe the same temperature curve, obviously this temperature readout doesn't mean much, because that is temperature which would be for the voltage you see on the left top screen for Lakeshore DT670 temperature sensor, but we are not using DT670, we are using LTZ1000 CH, which most likely will have slightly different curve. As of the temperature sensor from Lakeshore directly, I can show it. Let's see. On that module. So the original temperature sensor is located on, oops, camera stop. There we are. Right here. There is a die there on the ceramic substrate and very super thin wires that go towards the connector. So I can try to zoom in closer. There it is. That's where the temperature sensor is. In this beautiful gold-plated copper block. So I'll have to, it's attached with some epoxy. I'm not sure if I would be able to remove it without damaging the module. And I'll try to get the reading from that diode, so we can do some more tests with cryogenics. Let's see what we get now. Minus 70. I think we can conclude this video. So thank you everyone who watched and visited this live stream. and you can find a lot of test equipment and metrology and overall electronics related stuff on my website xdevs.com. So until next time, thank you everyone for watching. Bye.